if we have a population with some unknown parameter, how will we use a sample information to say something about that parameter? This is what statistical inference does, and that's what we are going to talk about today. Estimator and estimates. Point estimation is the same, if you want, to shooting at a target in sports. The estimator, which generates the estimates, is analogous to a tool used, which can be, for example, an arrow. A particular estimate is comparable to one attempt, and the parameter of interest is at the center of the target. Drawing a single sample from the population and using it to compute an estimate of the parameter is similar to shooting once at the target, at the center. Suppose we shoot once and we hit the center. Do you conclude that that person is an excellent one? Maybe not yet. But if that person shoots 100 times and hits the target every time, then we will consider him an expert. The idea here is that we cannot judge how good a point estimation method is based on a single estimate. Instead, we must see the results when the method is used several times. Because estimates are numbers, we can use them to create a frequency distribution of their values. And we need to assess how close the parameter of this distribution of the estimates is to the parameter of the entire population. That's what point estimators are about. Here are our definitions. The estimator T is a statistic which is a function of the values in a sample used to estimate a population parameter T. So T is a function or a rule that you apply to the values in a sample. An estimate T is the specific value of that estimator and is calculated for a particular sample. Let's assume random samples of size 3 are taken from a population X with mean mu and standard deviation sigma, or variance sigma squared. And I want to estimate the mean of the population. One rule I can use is the one that we used before, and it's more logical. I take the mean of the 3 variables. So whenever I get a sample of size 3, I calculate the mean. That particular mean, which is a number, is an estimate. I will write that T, if my estimator is T, will be x1 plus x2 plus x3 over 3. It's exactly what we wrote before. How do I know that my estimator does a good job? I would know that it does a good job if, after I generate a population from various samples, from multiple samples, the mean of that population is the same as the mean of the parent population. And I can check this by calculating the expected value of T. So applying the expectation algebra, I'm going to get a third expected value of x1 plus x2 plus x3. And I know that this parameter is linear and distributes, so I get 3 expected value of x. So it's 1 over 3 times 3 mu, so it's mu. It's exactly the same as the mean of the population. Therefore, my parameter, my estimator does a good job. It's a good estimator. We call it unbiased. What if I want to change my rule and I want another estimator, let me call it T2, to be x1 plus 2x2 plus 3x3, for example, over 3. Assuming I want to estimate the mean heights of all people in Hong Kong, and I take a sample of size 3, x1, x2, x3, and then I add the height of x1 plus 2 times the height of x2 plus 3 times the height of x3. Will my estimator do a good job? So if I calculate E of t2, I'm going to get a 1/3 expected value of x1 plus 2x2 plus 3x3. So I'll get 1/3. Expected value of x1 is mu, 2 mu, 3 mu. So I get 2 mu, which is not the same as a parameter I'm looking for. So I called T2 an unbiased estimate of mu, whereas T is an unbiased estimate, meaning it's a good one, of the population parameter mu. Can I fix T3 too? Yeah, I can fix it. I can take T3 as being x1 plus 2x2 plus 3x3 over 6. And then you'll see that the expected value of T3 will be exactly mu. So T3 is an unbiased estimator for the population parameter mu. So it's a good one as well. So if I want to estimate the mean height of people in Hong Kong, I can take the height of the first person plus 2 times the height of the second plus 3 times the height of the third and divide by 6. Would it make sense to do that? It's correct, but maybe it's not as efficient as ST because I give more weight to the person, to the third person in my formula. So we are going to see next how do we decide when an estimator is more efficient than another estimator. First, let us look at the definition of unbiased versus unbiased estimator. So an estimator T for a population parameter theta is unbiased if the mean of the sampling distribution of T equals to the parameter T, meaning that the mean, this is a distribution, sampling distribution of T, and its mean is the same as the mean of the population. It's exactly what we show on the previous page with T1 and T3. These two are biased estimators of theta because when you plot the sampling distribution of T, its mean is different from the mean from the population parameter. And in this case, same. So these one are biased. We are, of course, looking for unbiased estimators of T. However, as we saw in the previous page, we can have various unbiased estimators. How do we decide which one is better than other? Let's assume we have two estimators, T1 and T2, and the sampling distribution of T1 is that one, and the sampling distribution of T2 is the one on the right. We see that the spread of the distribution of estimates could be small or could be large. This suggests that the estimates found using the first estimator could vary, but they are close to theta, very less, whereas the estimates found using the second rule vary widely from the value of theta. Therefore, the first estimator, the one on the left, is more efficient. We define when an estimator is more efficient than other by the following. Please pause and read the definition. To summarize, we look at the two estimators that we considered on the previous page. They are both unbiased estimators for mu, as we saw, but the variance of the first one is smaller than the variance of the second one. Therefore, T1 is more efficient, which is in many ways logical, because why would you give more weight to one of the values? Let us look together at this question. You can pause a movie and try it. Question A. To show that T is an unbiased estimator of mu, I need to calculate the expected value of T. So I get lambda expected value of x1 plus 1 minus lambda expected value of x2. Remember, x1 and x2 are clones of the parent distribution, so I have lambda mu plus 1 minus lambda mu, which after opening the bracket and collecting like terms gives me mu. Therefore, T is an unbiased estimator of mu. B. Find the most efficient estimator. Basically, what this rule tells me, if I try to make sense of it and take values, is that if, for example, if I take lambda equals 1 over 10, tells me that T will be x1 plus 9x2 over 10. If I take lambda equals, for example, 1 over 3, will give me x1 plus 2x2 over 3. If I take lambda half, it suggests that it's the most efficient. I get T equals x1 plus x2 over 2. So that's what I need to prove, that actually lambda is 1 over 2 gives the most efficient estimator. So this was just me trying to make sense of the rule. When is an estimator most efficient? When its variance is minimum. So let me calculate the variance of T. And applying expectation algebra, I get lambda squared variance of x1 plus 1 minus lambda squared variance of x2. So I get lambda squared plus 1 minus lambda squared sigma squared. So I get 2 lambda squared minus 2 lambda plus 1 sigma squared. For the most efficient, this needs to be minimum. It's minimum when its derivative is 0. So if I differentiate, I get 4 lambda minus 2, which needs to be 0. Therefore, lambda needs to be half for the minimum value of that function. We, therefore, learn today what are estimators and how we decide that an estimator is unbiased. Amongst two unbiased estimators, we can decide which one is most efficient. I would like to remind you that an estimate is a value of the estimator. So if I take a particular sample and I calculate the value by applying the rule, which is the estimator, then I get the estimate.